Well, good afternoon, everyone. Welcome to our webinar this afternoon, presenting the preliminary results from our COVID-19 public transportation air circulation and virus mitigation study. This study was put together starting back in May of 2020 as a response to what we all are experiencing now globally with COVID-19 and its impacts on not just everyone's average lives, but the severe impacts that it's having on public transportation systems and transit agencies all over the world, really. We're very fortunate that we have the Fresno State Transportation Institute here in the San Joaquin Valley, centered at CSU Fresno in the School of Engineering. And it was thanks to that organization's existence that we were actually able to pull this team together to do this study. And we really want to thank FSTI. I actually happen to be an advisor with FSTI, and I'm very proud that FSTI was able to organize this. And Dr. Ali Tawfiq is the director of the FSTI, and he's here with me today, as well as the other team members that we have that worked on this project. So without further ado, I'm going to introduce basically the team. So as I said, we have Dr. Ali Tawfiq, who is the director for the Fresno State Transportation Institute. We have Dr. Defi Law, who is a professor at CSU Fresno in the Engineering and Mechanical Engineering Department. We have Dr. Yuri Grasas from UC Merced, who is a virologist and works at the UC Merced. I never can get that right, Yuri. I'm not going to try. What department? I know you're a virus specialist, so tell us what your department is actually.
Yeah, so I'm in the Department of Molecular and Cell Biology, but my specialties are in viruses, virology, and antiviral immunity.
Excellent, excellent. And last but not least, we have Mr. Mo Salem from Air2O. He is a respected mechanical engineer and HVAC expert, and his company does a lot of work with HVAC systems, or heating, ventilation, air conditioning systems. And so he was instrumental in all of the work that we did, particularly in the evaluation of the technologies that we use to try to find ways to mitigate virus spread within the transit buses that we were testing. So I'm going to kind of give it a brief outline of the webinar today. We're going to have a overview of how the project proceeded. We're going to talk about our focus areas of the research during the presentation. And last but not least, we'll have a Q&A session where people can ask questions specifically about the research that was conducted. And I will say that one thing that I want to point out is this project, and who am I? My name is Joseph Oldham, and I am a project manager and project facilitator for Fresno Metro Ministry, which is a 501c3 nonprofit here in Fresno, focused on community redevelopment, and with a heavy emphasis on expanding transit-oriented development. So really to move our communities forward and lower our greenhouse gas impacts and promote economic vitality across our communities, we need more transit usage. And COVID-19 has heavily impacted transit. And so our role here was to act as a liaison with the transit agencies that we worked with for this project. And we want to give special thanks to Fresno County Rural Transit, as well as Clovis Transit, for providing their facilities and their buses for this testing, and all of the assistance that their staff and management gave to this project to move it forward. We had a very limited budget and we had a very limited time frame. And without their assistance, we couldn't have done this. So with that, I'm going to turn it over to Dr. Ali, and he's going to kind of take us to the next level.
Thank you, Joseph, and thank you all for being here. So as Joseph mentioned, we're planning we have an overview presentation of the project, and then we have specific more detailed presentations about different tasks of the project. So Joseph and I will present the overview presentation, and then I will have Dr. Law present the details about the airflow experiment, and Mo will present details about the specifications of the devices and equipment we tested. And then Dr. Gassis will present the information and details about the virus mitigation part, the experiment and the results. And after that, we'll have an open Q&A session. We think that the whole overview presentation is not going to take more than 25, perhaps 30 minutes maximum. So hopefully we'll have almost an hour to take and answer questions that you may have. Feel free to type your questions in the chat box at any point in time. However, we will not start answering them till after we complete our presentations. So with that, I have shared the screen for the PowerPoint overview presentation PowerPoint. Can you all see that? Mm-hmm. Okay. Yep. All right. So our outline is divided into 3 parts: background about the project, which Joseph already mentioned some, summary of activities, and results. So I'll ask Joseph to present the first few slides, then I'll present the results.
Sure. So basically, this was our background. We were really interested in understanding what airflow patterns existed in existing transit buses, recognizing that while at the time the CDC hadn't fully acknowledged that COVID-19 or the coronavirus, SARS-CoV-2, could be an airborne virus and be transmitted by airborne transmission, we basically recognized that this, because of the size of the virus, that this was highly likely. And understanding how airflow inside of a transit bus could contribute to infection was really one of the key points and reasons why we wanted to move ahead with this. Airflow in transit buses was not well known, but it is critical to understanding how people can be infected, both passengers and drivers. We also wanted to look at the opportunity for various technologies to be deployed as retrofits into existing buses and potential into new bus designs, recognizing that while SARS-CoV-2 is our key focus right now for viral infection, there's been other viruses in the past that have threatened to become at a pandemic level. And it would be naive of us to think that SARS-CoV-2 is the last of the viruses that we'll have to deal with that could create a pandemic. So we assembled a broad team for the project. As I mentioned, the Fresno State Transportation Institute took the lead with this, Dr. Tawfiq, Dr. Law. Then we reached out to UC Merced, and Dr. Grassis agreed to be a participant in the project. Of course, I was kind of one of the early folks that kind of discussed this with Dr. Tawfiq. So I said, okay, yeah, definitely I'll be a part of this. And then Dr. Tawfiq had a relationship with Mr. Salam, and so we brought him in as our HVAC consultant engineer. And I had already been doing some work with Fresno County Rural Transit, and they are also an advisor for the Fresno State Transportation Institute. So bringing them into the project to provide the buses and the platform for our testing was actually fairly easy. And then I'd also had a relationship with Clovis Transit, and so therefore it was easy to actually reach out to Clovis Transit and work with Amy Hance, who is the general manager for their operations, and they were just thrilled to do this as well with us. So our tasks really boil down to conducting field tests in actual buses, looking at airflow patterns, conducting measurements of the airflow at various locations in the bus, looking at viral spread mitigation using live virus, which no one had done before, and then conducting computational fluid dynamic modeling using the readings from the airflow testing. And some of the here's some of the testing that we did. And let's see, Ali, do you want me to continue with this, or do you want to have some conversation?
Sure, I can pick up. So for the airflow testing, we tested with 5 different buses, both, as Joseph mentioned, with the Fresno County Rural Transit Agency, as well as City of Clovis Transit. For the airflow, we tested with anemometers, airspeed meters, as well as non-toxic. We video recorded the spread of non-toxic colored smoke, as well as steam inside the cabins of the buses, and then we did the analyses of these based on these video recordings. We tested under different vehicle operation conditions, so with the vehicle stationary or in motion, windows open and shut, door open and shut, HVAC on and off, HVAC with fresh air on or off, emergency hatch open and shut, as well as with the smoke or steam starting at the rear, middle, or front of the bus. So we did a bunch of experiments, and our objective was to see how fast would the virus spread and how fast it would clear, and if there's any measure that we could adopt to ensure that things are safer. So for example, does it help if we open the windows or if we open the emergency hatch? We also, Dr. Law is going to talk about the CFD model that we built. So that was the airflow testing part. For the virus mitigation part, we tested, we measured the existence. So we released the virus in the bus, and then we measured its return through the vents as well as on different surfaces. We used 3 different live viruses. Dr. Grass is going to talk about the details of this. One of them actually flew all the way from Germany, so did more traveling than I did this summer. And then we tested a bunch of different technologies. We tested photocatalytic oxidation filters and inserts, UV light, HEPA filter, both MERV 17 and 19, positive pressure, under cooling and heating, and we tested with antiviral materials. And Mo Salem is going to present the specs of these different technologies in a little bit. We tested most of these experiments both in the lab and the field. Initially, we got some really good results in the lab, so we got excited and we got concerned at the same time, because we wanted to make sure that our results are actually meaningful. So when we did and repeated these tests inside an actual bus in the field, we were very excited that we got highly consistent results. So that gave us a much higher level of confidence in our conclusions. These are some pictures of the testing. So on the left side, you'll see the air meter tests, and on the left side, and the smoke or steam coming out. On the right side, you'll see us spraying the virus at the return of the bus, return of the HVAC inside the bus. And this is one of our students who is helping Dr. Grasses, or helped Dr. Grasses in one of the experiments. So at the end, our results, we have results for the HVAC and we have results for the virus mitigation. For the HVAC, we noticed that the virus spreads much faster than it actually clears. So on average of all experiments, the speed of clearance was quadruple, not speed, the time it took to clear was more than quadruple the time it took to disperse. And opening the windows, every condition resulted in different times. So opening the windows had an impact, but the impact was different if the bus was stationary versus the bus was moving. It also, if the bus was moving, it helped clear the air faster, a little bit faster. It also helped spread the virus or the smoke away much faster. At the end, the time it took to clear was, on average, much higher than the time it took to spread. So our conclusion at the end of the airflow was that to make it safer, we have to find a way to use technology to actually clear the virus from inside the cabin. With that said, the city of Clovis, this picture is a barrier, plastic barrier that the city of Clovis did for their drivers. And what we noticed is this cutaway bus, two different HVAC systems. It has an HVAC system in the chassis where this is located. So by sealing this area, the air that the driver is receiving from the chassis HVAC is different from the air that the passenger are receiving from their own HVAC at the rear. So if we added positive pressure, so we turned on the fresh air inside this compartment, and we noticed the compartment was pressurized, and then we also released smoke back in the cabin and tested to see if the smoke would get in, and it did not. So our conclusion with that, such systems, we think that such solution would protect the driver, but obviously not the passenger. So we still need a method to make the air safer for the passengers. On the passenger side, so we tested the virus mitigation inside the HVAC system, and this is how different technologies did. And we report the technologies both as against all viruses, how efficient was this technology against all viruses, because as Dr. Grass is going to present, viruses are not the same, as well as the 5/6 virus, which is the one that's most similar to the corona. The reason we report against all viruses is because we hope these technologies could help not just corona, but any airborne virus, such as the flu or any other ones that may appear in the future. So we'll notice in this that the photocatalytic oxidation insert performed the best, and second, pretty close, was the UPC light. And I'll not mention more details. I'll leave this for Dr. Grasses. With respect to the surfaces, because we also tested with surfaces, creating a positive pressure of half a water inch inside the cabin prevented the viruses from settling on surfaces by 100%. So that was quite impressive. And we also tested with copper antiviral materials, copper foil tape, as well as copper infused fabrics. And we noticed that the impact on the 5/6 virus was outstanding, so it mitigated 99.7%. However, the results were not the same with the other two viruses. At the end, we are very excited about these results. We think they would be helpful. Our final report is not ready yet, so we decided to release our results before completing the final report, because we think that they would be helpful for our community. That said, we had our prelim reports. So before releasing these results, our prelim reports were reviewed by 2 external reviewers. With that, I will ask Dr. Lowe first to present details of the airflow experiments. And afterwards, I'll ask Mo to present details of the specs of the devices. And then Dr. Grasses to present details of the virus mitigation experiments. Mo, do you want to share your screen? Sorry, Dr. Law, do you want to share your screen?
Sure. I pre-recorded my slide. Let's try that, and then I'll let it run, and then
For my CFD models, large amount of effort is spent on profiling the interior geometries of the buses, including driver and passenger seats, windows, supply air diffuser and slots, exhaust grills, stairs, driver's dashboard, and storage area. My CFD models use species mixing model to simulate the air circulation and mass transfer behavior. 2 equation capsule turbulence models used to simulate airflow turbulence. Inlet and outlet boundary conditions are specified from the field measurements. For example, air velocity, relative humidity, and air temperature are measured at the inlet air diffuser and slot and outlet exhaust grill locations.
yes, I will address that in the following slide. Let's go to the next
Moving
slide.
bus simulation. This slide presents 2 different bus configurations. Bus A is compressed natural gas power, whereas bus B is electric power. Bus A's return air duct is located at the back of the passenger compartment on the rear wall over the rear seats, whereas the bus B's return air ducts are located in the ceiling over the wheelchair position behind the front axle closer to the driver's station. Both of these bus designs used continuous supply air ducting in the ceiling, as you can see from pictures, next to the windows with slots over every passenger sitting in row in the bus. Driver's air supply was by multiple adjustable vents over the driver's sitting position in front of the bus, supplied by the same ducting as the passengers. The 35-foot buses tested had different design for the window opening. Bus A had small sliding windows above larger fixed window, and Bus B has somewhat larger bottom hinge windows above the large fixed one that open inward at the top. Both buses are around 99 meter long, 2.5 meter wide, and 1.5 meter tall. Figures in this.
Okay, so this slide shows that the plume is going from the ceilings to the ground and then from the air circulations. So this is showing the water vapor concentrations from the CFD models at around 28 seconds for both buses. This is the CFD results.
Figures in this slide, and this is the visualization done experimentally. This slide shows both smoke on the left and steam on the right visualization of the interior stationary bus A when viewing from the front. Likewise, the experimental visualization displayed the plumes moving from the ceiling of the bus cabin towards its floor and forming the air circulation. So both numerical and experiment visualization demonstrate qualitative agreement between each other in terms of the air circulation patterns. This video shows a smoke visualization.
Yeah, got very dense.
This slide.
And so this one shows the gas tracer evolutions in CFD models for both buses at different times. So 19 seconds, 28 seconds, 38 seconds. So you can see the bus B has a greater concentration because to begin with, based on the field measurements, the concentration of water vapor is greater based on the relative humidity measurements. So you can see how the gas tracers move around throughout the bus and how they evolve over the time. So they fill up the bus throughout the entire bus quickly in terms of seconds. So that's what the in the experiment from the field measurement found as well, is close to around 40 or up to 50 seconds to fill up the entire bus. So it's kind of similar in terms of the qualitative agreement between the CFD and the experiments.
This slide presents the evolution of the gas tracer using the water vapor for both buses in motions with passengers windows open. All in motion testing was done at a highway speeds of between 50 and 60 miles per hour. The 35-foot buses tested while in motion had different design for the window opening. Bus A has small sliding windows, whereas Bus B has a larger bottom hinge windows. Bus A shows some gas tracer concentration, whereas Bus B has minimal gas tracer concentration inside the bus. Bus in motion with passengers windows open has significant effect on Bus B, as we can see from the pictures, in terms of clearing the aerosol concentration that can carry the virus. This slide shows the comparisons of the Bus A when it's stationary with passenger windows closed and moving bus with passenger windows open. We can see that there's minimal difference between those two bus conditions. However, for bus B, there's a significant difference between stationary and moving bus conditions. The water vapor or aerosol concentration diminishes when the bus B is in motion with passenger windows open. However, the driver's compartment is still very much unaffected by the moving bus configurations. It still has considerable concentration of water vapor that can potentially contain viruses in it.
Okay, generally the virus contaminant spreads throughout the bus in seconds, like I mentioned. From our findings, it takes approximately 1 to 3 additional minutes more than the spread time to clear, especially when the bus is in motion and with windows open. Operating the buses with windows open does not provide much benefit, but it does reduce the time to clear from our findings. And then bus retrofitted with the plastic enclosure for the drivers can protect the drivers from the virus released in the passenger compartment. And so that's a very good thing to notice. I will pass over this time to Dr. Grasses.
Thank you, Dr. Lowe. So I will hold on answering the questions. So we have 2 more short presentations, and then we'll start answering questions. So Mo, do you want to share your screen? So Mo now is going to present the specs of the devices we tested for virus mitigation. Mo, if you're speaking, we cannot hear.
Yeah, I was mute, sorry. The first device we tested was HEPA filters, and we tested 2 types of HEPA, MERV 17 and MERV 19, with also 2 different thickness, 2-inch and 12-inch. Obviously, the 12-inch was a little bit challenged because pressure drop was tremendously high into the bus. And early on, we understand that it's not a really a very good solution because that would require modification of the air conditioning of the bus itself. However, we tested it anyway. HEPA filter work great in particles. In fact, we noticed almost 80% to 90% reduction on the particle numbers of before and after HEPA. However, they did not perform great on a virus mitigation, and that is because viruses have less diameter than regular normal dust or bacterial particles. So we expected that we don't gonna see a very good result from HEPA, and finding was pretty much conclude what we expected. The second technology we tested, which is a UV light, and to be honest, that was a completely surprise. UV light required a long dwelling time to kill viruses, and just using them by itself, we were not quite sure how they will really operate. We combined them with a standard carbon filter to kind of slow down the airflow to allow the UV to work. And to our surprise, they perform very, very, very well on a virus mitigation. In fact, they rank number 2 in our virus mitigation device, and Dr. Yuri will explain that in a minute. Even so, we haven't used a very sophisticated one. We use pretty much off-the-shelf UV light, and we put them. We still need to investigate more if we adding a different filter to the UV light will operate well or not. That's to be found. The third technology we use is a photocatalyst filters, and basically we call them filter because they're flat and they look like a filter, but they're not really a filter. They don't do any type of filtration. They rather kill the virus. And mechanism for photocatalyst is very interesting. The way it works, we do have a medium that actually covered by titanium oxide. So when the water vapor from the air go over the titanium oxide medium, the UV light inserted between the in the photocatalyst filter will catalyst the reaction to release OH free radical, hydroxyl free radical. Those free radical eventually will actually catch the virus and kill it. They kill anything alive. It's just like a hydrogen peroxide for the lack of a better term. It's literally like a hydrogen peroxide will kill anything alive. The good thing about free radical or OH, they have a very short lifespan, half-life, so they don't move outside of the filter area or outside of the compartment area, and that was obviously PC photocatalyst filters actually performed very, very well. They were, I believe, ranked number 3. The third technology we use, it's again photocatalyst. It's just a different setup. And the way we did it, we wrap the UV light with the photocatalyst media rather than have it surface. And in a minute, I'll explain the difference. But because of that, we generated a lot more OH because of the light catching almost every place of the titanium oxide. And in fact, this particular device ranked number 1 in our testing. And we work closely with the manufacturer to design it and insert it. And we believe that will be a very valid option for public transportation. It's easy to work with, and it's very simple and small. Last but not least, we also tested electronic ionization filters. And to be honest, we was not very pleased by the final result that it offered. It's a lot of hype about it in the market. However, when we tested, it did not mark very well from both sides, either particle-wise or viruses-wise. In fact, it was almost like any other device or any other regular filter. In fact, UV act better than a regular ionization filter. One thing I just want to explain about the UV light, and we'll talk about that later, the difference between the insert and the filters, that the filters, you have your media on the side, and after that you have light. So the light intensity actually go very high under the light bulb, and it goes low as you stay away from the light. So you have almost a dead zone between each light that will release less OH radical, and that is why we believe this setup, when we have the titanium oxide wrapped around the light, it acts better, and we believe this way it releases more OH, and that's why it ranks better. Just a quick overview about the different technology we use. Having said that, I'll give the mic to Dr. Yuri. He will explain what is the result for those particular or for those different technology ended up in the experiment. Dr. Yuri?
Thank you, Mo. Can you stop sharing the screen, please? All right, Dr. Grasses.
Okay. Okay, hello everyone. So my name is Dr. Yuri Grasses. I'm an assistant professor of virology and antiviral immunity at the University of California, Merced. So I want to start by expressing 2 key aspects to the study. The first is that this is a collaboration between engineers and biologists. And oftentimes when we're seeing these sort of studies, it's either one or the other. And so what's nice about this study is that we're trying to combine both. The other thing that we're trying to do is actually work with viruses, actually look at how viruses act according to how these devices are used and how infectious these viruses are after exposure to these devices. So that made it quite challenging. And so what I want to express at first are the different viruses that we used. So for comparison, on the left-hand side, we have the coronavirus that we're all trying to mitigate right now. Its size is about 130 nanometers. It has an RNA genome, and it has a lipid covering, okay? And so we wanted to test, because we can't spray the coronavirus onto a bus, or I certainly don't want to be exposed to it in any way. We decided to use 3 different viruses that normally infect bacteria, right? So these viruses are infectious to bacteria, but not infectious to us. And so we use 3 different viruses. We use the Phi6 virus, which is most similar to that of the coronavirus. It has a similar size, it has a similar genome, and it also has lipids on its surface. And that was the virus that we had airshipped all the way from Germany. The other 2 viruses that we tested are common bacteriophages. These are viruses that infect bacteria, T7 and MS2. T7 is a very hardy protein shell. It has a size of about 105 nanometers. It has a DNA genome as opposed to an RNA genome, and it does not have any lipids on it. MS2, by contrast, is a very small virus. It's only about 30 nanometers in diameter. It has an RNA genome, and it does not have any lipids on it. So to summarize all the total mitigation from all the experiments that we did, so I'm starting with this, and I'll get into more details about some specifics later or in the subsequent slides. What we're showing here is the percent mitigation of infectious virus. So what we did in these experiments is that we would actually spray the virus with a spray bottle into the intake of the HVAC system. The devices were placed within the HVAC system. They were allowed to move through the HVAC system, and then we would collect with open air filters at certain locations, and then we'd also swab at certain locations throughout the bus or in the laboratory setting. So under normal cooling conditions, what we see here on the bottom, under normal cooling conditions from all the experiments, you would still see some amount of viral mitigation from all the viruses, upwards to about 75%. Heating in all the experiments increased the viral mitigation as you increase the temperature of your HVAC system. The HEPA filters themselves, as you increase the amount of filtration, were also good at mitigating the virus, infectious virus. As was mentioned by Mo, when you start using UV devices, as we're showing here in yellow and in green, UV devices such as the photocatalytic filter or insert were very effective at mitigating all these viruses, as was just simply the UV light combined with the carbon filter. The carbon filter itself was not any more effective than simply cooling conditions. Using ionization was effective, but not as effective as the other types of mitigation, as was positive pressure created within the bus. So specifically, since Phi6 is the most similar virus to that of a coronavirus, we're showing the results just from Phi6 in all experiments, and the same results apply. That is, under cooling conditions, about 80% of the virus was mitigated, and then as you increase temperatures, you see an increase in mitigation. The virus was affected by HEPA filtration, though not as well as treatments or devices with UV light. You see in this case, these 3, the bright yellow, the darkish yellow, and the darkish green are all UV containing devices, and they all work spectacularly. The ionization, again, worked, but not as well as the others, as did positive pressure. And now to go into more specifics about this, within the lab itself, we were able to control the total input and output, and so you'll see some, some very definitive results in these laboratory settings. On the left-hand side, I'm showing you the total viral mitigation. On the right-hand side, I'm showing the Phi6 mitigation. And so what you see here is under cooling conditions, and the total mitigation is about 60% of the viruses were mitigated under just normal conditions. As you increase the temperature, again, you see the amount of viral mitigation. And then HEPA filtration didn't seem to work even as well as simply heating the HVAC system. The UV conditions, again, whether it was a photocatalytic filter or insert or a carbon filter with UV light, were very good at mitigating all the viruses, as was the ionization. Phi6 particularly supported these same ideas. So if we looked at that just specifically, it seemed to get mitigated or trapped perhaps a little bit simply under cooling conditions. Heating did affect it, as did some very strong HEPA filtration. the photocatalytic insert worked the best on Phi 6, and other UV treatments actually worked well as well. And then if you go out into the field and you did this work on the buses themselves, we combined the data from bus A and bus B. You'll see that cooling conditions affected the total mitigation, and in Phi 6 in particular. And then heating, either at 83 degrees or 103 degrees, had an effect on the total mitigation. But again, when you start to see the presence of UV treatment, this is where things were almost eliminated completely, right? Above 99% of the viruses were eliminated. And then specifically, that was also the case with the Phi 6, the virus that most resembles the coronavirus. So we did those studies by taking filters at the outputs to determine, where the viruses were coming out and how much virus was there. We took those filters back to the lab and we tested how infectious those viruses were after treatment. The other part to this is that we actually tested, by swab throughout the bus and determining how much virus had actually settled in any one of these cases. And so I'm showing you the data for all the viruses, and how well the viruses were mitigated by each of these conditions. Cooling had really no effect, right? That is, the viruses settled. Everything was, as far as the viruses were concerned, they were settling completely onto surfaces under normal cooling HVAC conditions. As you increase the temperatures, settling was mitigated. That is, you did not see as much settling on the surfaces as you did prior. Same with HEPA filtration and with the carbon filtration with UV light. The photocatalytic filter and insert had an effect, much greater than that of cooling, of course, but not as much as say, HEPA filtration or UV light with the carbon filter. The last thing I'd like to point out here is that positive pressure, that is creating a positive pressure environment within the bus, right? So pushing air out, completely eliminated settling of viruses onto any of the surfaces. And lastly, we're still working on this data within the lab itself. But we're testing different types of fabrics that could be used to help mitigate the viruses as they settled on the surfaces. And so we tested different polyester and different cotton, and then amounts of copper with either polyester or cotton. And then again with graphene, and then just on a steel surface versus that of a copper foil surface. And what you see here is under, say, 100% polyester or 100% cotton, or a blend of both, there was, not much mitigation, right? However, if you added copper to the presence of either polyester, the more copper you had, nearly 100% copper polyester, or 40% copper or 25% copper with polyester, you saw a very increased amount of viral mitigation according to how much copper was present. Same results applied with that of copper added to cotton fabric. Okay, and lastly, and very importantly, most of our surfaces are coated with stainless steel. So we tested that in comparison to copper foil, and copper surfaces absolutely mitigated Phi 6 in a way that we couldn't even really detect it. The results for the other two viruses were very inconclusive. They just didn't show us much differences in results, but we're still working on that in the lab. So to conclude, we saw very consistent results between that within the bus and the lab. And in normal cooling conditions, you could see that mitigation of the viruses were upwards of 85%. However, this still means that there's about 15% of the virus that could still be spread throughout the bus. So it's important to try to encourage the use of these devices. our suggestions would be to use a UV type system, either UVC light alone or in combination with photocatalytic inserts or filters, because this is very good at eliminating all of these types of viruses, and specifically a virus very similar to that of the coronavirus. The photocatalytic filters were very efficient, as were the other devices that were using UV lights. And the trouble, and one of the nice things that we did here was we didn't just look at one virus. We looked at different size viruses of different genomes, different structures, and we looked to see how these devices could affect different things. And I think this is important when we think about respiratory viruses spreading throughout an HVAC system. And what we found is that, the smaller the virus, the more difficult it was for us to get rid of, but they were still able to be mitigated, okay? And in combination, higher HVAC systems, heating temperatures could help to mitigate large percentages of the viruses, so that if that is used during the wintertime, this will help actually mitigate viral spread. And that's all I have to present for today, so I'll pass it back to Dr. Tawfiq.
Thank you, Dr. Grassus. All right, so last thing I want to share before we open it to question is that we have summarized all these results. We produced an infographic, so I'm going to share my screen now. So with our main findings, so this is the infographic that we created, and it's showing the results of the air circulation, the dual HVAC bus systems, the viruses that we tested, the two most effective technologies. And we point out that these technologies only clear the virus once the virus reaches the HVAC. While virus is traveling from the source to the HVAC, we did not test any technology that would protect passengers or drivers in this time period. So that's why we think face masks should always be the first line of defense. This is the summary of the air virus mitigation in the air, and on the right side is the summary of virus mitigation on surfaces. As Dr. Yuri mentioned, since heat alone mitigated larger percentages of the buses, we think that transit ridership could be safer in the winter, since the higher HVAC heating temperatures alone mitigate larger percentages of the viruses. And last, we think that these results could be equally valuable for any confined space with HVAC, being at a house, offices, shopping centers, classrooms, courthouses, and so forth. And with that, we'll open it up for questions. I know we have several questions in the chat, so I'm going to read them one by one and direct them to our team. So the first question was by Tyler Baker, and he's asking, please elaborate on the finding that positive pressure mitigated the viruses on surfaces by 100%. Are you referring to positive pressure of the whole bus? Mo, do you want to answer this one?
I can answer this one, yes. Exactly what we did add an external air source to the bus. Basically, we add a fan that can actually push more airflow into the bus, and we measure the static pressure inside the bus, and we were able to increase it by ½ inch of water column. And that then we take tests with the swap. When we added that extra pressure into the bus, that will allow the virus to be pretty much mitigated from settling into the surfaces. And we believe that could be achieved by allowing more fresh air enter through the HVAC system to be pushed into the bus. It's a simple measure. Obviously, it could impact the fan power into the bus, and we need to study that carefully. But by allowing more fresh air to go into the bus, that could really help the mitigation of the viruses into the surface. And yes, we measure the static pressure of the overall bus, not just inside the air conditioning system.
Excellent, thank you, Mo. Second question by Jim Fox. Can you clarify what the make, model, and size of the buses were that you used in the tests? I'll answer this one. We were asked not to disclose the actual buses we used for testing. And that's because our objective is not to interfere with the private companies' competition in the market. Our objective is just to help the market to make transit, restore transit ridership and make it safer. So I apologize that we will not be able to answer this question. Another question by Jim Fox. Can you identify the photocatalyst oxidation system you used in the test? Was it from a third-party manufacturer? I'll answer this one too. So yes, so we used devices that are readily available in the market. We may have done small tweaks to them, but yes, we believe these devices are commercially available right now. The next question is by Tom Sullivan. I hear photocatalytic creates formaldehyde. Can you advise? Mo, can you take that one too?
Can I share my screen, please?
Yes, you can.
Okay. So that is a very valid question, actually. Yes, formaldehyde is. You guys see my presentation?
Yes.
Okay. Yes, the formaldehyde, it could be a byproduct for oxidation, formaldehyde oxidation for the titanium oxide. It is true. And the reason for that, it is incomplete oxidation. And we discover also when you have a flat surface and when you have light, when you have low intensity light around those areas, that when you could get more formaldehyde. But in fact, we're trying with the team to investigate that more in a different study or upcoming study. We believe that when you have a decent density of the light around the titanium oxide, the formaldehyde will be completely mitigated, but that yet to be verified. That is one of the really important things we need to study, but that's just part of the thing. So yes, what you heard is true, but we also believe that it is not. It is a design problem, not a technology problem. So if we tweak the design, we could completely avoid that problem.
Mm-hmm. Thank you, Mo. And I will add to that. So these devices or technologies that we tested are commercially available, so they are already in use in the market. So while we think it's safe because they are already in usage in the market, we have not tested this ourselves just yet. Next question is by an anonymous attendee. How much virus was released on the bus, and did bus seating capacity play a role in that? Just thinking about potential infected passengers and how much each person could release in the air, if that matters. Dr. Grasses, do you want to take that one?
Yeah, that's a great question. It does matter. How much exposure you get to a virus really dictates how severe your symptoms might be. And so we did take this into account. It seems that in a heavily infected person, it's usually tens of millions of viruses are expelled upon a sneeze. Right, and then that's what gets distributed amongst the air. So we used just above that level. We used hundreds of millions of viruses when we did these experiments. In large part because when we tried to originally do it in the tens of millions, we weren't able to really get results, and we wanted to actually see that these devices were working in some way. Having said that, I still believe that the experiments are valid in that if someone is continually sneezing and spraying tens of millions of viruses, hundreds that accumulate into hundreds of millions of viruses, this is exactly the range that we were testing. And that's also what gets distributed amongst the bus and what someone who might be, say, the driver could be exposed to for hours at a time, okay? So I do believe that we were working within the range of what you might be exposed to on the bus.
Thank you, Dr. Grasses. Adding to this, nobody knows how much virus causes infection. So whether it's tens or thousands or millions, so I think nobody knows the answer to that just yet. And that's why I think it's important that we try to mitigate as much virus as possible so that we can be as safe as possible. All right, so do we have another question for, I think it's for Mo. Ahmed Jamal is asking, through Mo's presentation, he has mentioned that to have such results for the carbon filter and the UV, we had to increase the dwelling time through the combination. How the same took place in details, please. Also, how the same affected the efficiency of the AC system, as well as the airflow rate and velocities.
Okay, well, definitely a UV light in the airstream need more dwelling time to kill viruses. It doesn't happen instantly. And we know most of the phase velocity within the HVAC system, we're looking about 500 feet per minute, which would translate to 2.5 meters per second. And that in that rate, UV light alone will be useless. And in order to try to fix that, we install a carbon filter with high density carbon filter to slow down slightly the air around that to allow the UV light to have more dwelling time over the virus. I can see your point, how that will affect the overall system. It could, because that could increase the static pressure of the fan, and that's yet to be studied. It could not work with a smaller system that already have a very short span for static pressure. It could affect it and not going to be very well. And that's why photocatalytic insert actually work better, because it doesn't need that dwelling time. But I can understand where you're coming from. Definitely, in order to use a UV light with a carbon filter, your fan must have a little more capacity to allow that extra static pressure into the HVAC system. Go ahead, Ali.
Thank you, Mo. So this question, I think, is better suited for Dr. Grassis. So question by Henry Pan. So if fabric or any surface was treated with copper, it would be effective in killing the virus. Is that correct?
Yeah, so we're testing this now with these bacterial viruses, so it seems that copper is a very effective antimicrobial agent. It's very effective at killing off bacteria and killing off viruses, and so we're continuing these studies in our lab right now. But copper's been used as antimicrobial for millennia, and using metals such as brass would be very effective, and if you consider using fabrics that have copper in it, I think that would be a good use to kill off viruses.
Thank you, Dr. Grassis. I think the next question is also for Dr. Grassis, also from Henry Pan. How did researchers determine 5.6 is similar to SARS-CoV-2? Is it based on how both viruses are structured? Why not use similar viruses in the SARS family?
That's a great question. So 5.6 is just the most similar type of virus that we could use. If we used a coronavirus or coronavirus-like virus, there's a couple problems. One, we could get infected ourselves, or if we used an inactivated virus, then we couldn't really determine the infectivity and the effects of these devices against the coronavirus itself, right? So as much as I would love to try it, I'd prefer not to work with the coronavirus or anything from the coronavirus family themselves. So we used 5.6 in large part because of its great similarity in size, great similarity in structure and its formation and the type of genome that it has. So if it has a similar genome and a similar structure, it could be affected in the same way that the coronavirus would be as well. And we are continuing studies to determine how effective, say, the UV affects this 5.6 as compared to that of the coronavirus, and extending these studies further.
Thank you, Dr. Grassis. And to add to this, this is the reason, one of the reasons, because we recognize that the 5.6 is not the coronavirus. That's why we tested with 3 different viruses. So if we think as our technologies can kill 99.4% of all these viruses in all experiment settings, then we see very little chance that it would have a different effect on the actual coronavirus, or the flu for that matter. Next question by Henry Pan. For buses with single HVAC systems, what impact did plastic barriers have on spreading potential viruses to the operator? Joseph, do you want to take this one?
Sure, glad to. The quick answer is none. So if it's a common HVAC system that's providing air for both the driver and the passengers, plastic barriers are pretty much useless. The plastic barrier that was effective and that we showed in the presentation was on a cutaway bus with a dual HVAC system. The OEM chassis had an HVAC system that supplied the driver area, and then there was a bus body supplied HVAC system that supplied the passengers with conditioned air. And the way the system worked that Clovis put together was they completely isolated the driver's compartment. And the way that that was safe was when the driver would turn the HVAC to outside air only and not recirculate, it literally pressurized that compartment and then prevented any airflow from the passenger compartment into the driver compartment. So it was only that ability to pressurize the driver's compartment with outside air and not allow any penetration of air from the passenger compartment that provided any kind of safety for the driver.
Great, thank you. Question from Stoil Pamukov. I apologize if I mispronounced that. Is the PDF summary document available for download? Yes. So the PDF document is, we created it for circulation. So it is, if you email Rebecca Was, the person who sent out the announcement, or if you email me, I'll be happy to email it to you. But we have created a web page for the project on our Fresno State Transportation Institute's website, and it should be live later today, if not already, and we'll have the PDF on the website. Next question is by anonymous attendee. To follow up on the question about viral load and potentially multiple passengers infected, would your studies suggest anything about limiting seating capacity on a bus? I will take a stab on this question, and then if anybody has a follow-up, please follow through. So I do not think our studies can be used to answer this question. I think our focus was how can we make the air cleaner, and in any setting, whether it's with no limiting capacity or with half capacity or quarter capacity, adding these technologies would make it safer. So that's what I think. Right now, we're pursuing other grants to study this in more details, so that we can investigate the spatial distribution of a virus around the source of a spreader and see how the masks affects that. So hopefully, if we get that grant, I think we'll be able to answer. Right now, I do not think I have an answer. Does anybody else would like to add to that?
Yeah, I think that there's a lot still unknown about how much viral virus is expelled by an infected patient. That even can be widely variable that we've seen so far, and how the accumulation might be within a bus. Having said that, there are mathematical studies that have been released where if you have, say, 100 persons in a group of 100, the likelihood in any particular region, how many people might actually be infected, right? And so right now, in some regions such as us in the Central Valley, that could be as high as 40% within, or 40% chance that someone is infected within a group of 100, excuse me. So a 40% chance that someone is infected within a group of 100. So we can't really answer this question. I think there's a lot more variables that the field as a whole needs to figure out.
Thank you, Dr. Grasses. Anybody else like to add to this question? All right, moving up to the next question by Stoil. to what velocity did you have to slow down the airflow by the carbon filter to see benefits of the UV? No?
I can answer that. Definitely below 350 feet per minute or around 350 feet per minute. I'll see the lower will be better. And that's what represents the challenge. Really, we're using a UV with carbon filter, but that is what usually we tested. We tried to test it at 500 feet per minute, but on a lab setting, we was able to lower it a little bit, but definitely around that 300, which is about 2 meters per second to 2.1 meters per second in that range.
Now, to add to this, we did not test with different velocities. So we're not saying that that's the only velocity where the UV light would function. That's just saying this is the velocity that we tested, and we did not test with different velocities. One more question by an anonymous attendee. A follow-up question about use of Phi-6. Since the start of the study, in terms of what we know about SARS-CoV-2, have there been any scientific findings that suggest Phi-6 is either a better or worse mimic than originally conceived? Dr. Grassus?
Sure. Phi-6, actually, we know more about Phi-6 than we do know about the coronavirus. And so there is information about how Phi-6 reacts to, say, UV exposure and to different types of metals. And that's what we're learning now with the coronavirus. So as we're learning from the coronavirus, we're finding that Phi-6 is actually a really good proxy for testing and comparing to that of the coronavirus. The more we learn about the coronavirus, the more we're learning that it has similar features and responses to that of Phi-6.
All right, so I think these are all the questions I read in the Q&A. I'll check the chat if we have questions over there. Attendees, I'm writing on a vehicle. Can you clarify the model of the buses? So we cannot say the make and the model of the buses. The buses that we tested for airflow ranged from large 35-foot buses to cutaway buses, small cutaway buses. Dr. Lowe answered the question. The bus fee, how does positive? All right, so there is a question from Brian Sherlock. How does positive pressure prevent settling? Is it increased air velocity and turbulence, increasing settling time to longer than the residence time? Did you examine high dose UV only? Mo, do you want to take this one?
The exact mechanism why positive pressure prevented settling, we don't know. However, we have a hypothesis that a turbulence near the surface prevented the virus from settle, because the air has to go out because you have a positive pressure, and obviously the bus is not a balloon. So a turbulence near the surface prevented any settling of the viruses, but the exact mechanism is not determined yet, but that's our hypothesis, and it could be a further study about it.
And did you examine high dose UV only?
We did not.
All right, next question is from David Carroll. It seems counterintuitive that opening windows does not reduce spread. Should bus operators stop encouraging passengers to open windows? So I'll take this one. So opening the windows makes the spread happen faster. So it increases the circulation speeds in the bus significantly, and the spread happens much faster. The clearance also happens faster, a little, but still clearance time has consistently been much longer than spread time. Does anybody want to add to this?
I believe I want to just add question. When we experiment that, we actually had to drive and also make it spread. When we did the moving test, when we opened the window, creating the laminar flow next to the window to kind of take the viruses and hit the the air in the back and forth, it created a lot more turbulence, and that is believed that is why created more spreading. If that will help in a settling on the surfaces, we do not know because we haven't tested, but it's really counterintuitive. It's, yes, opening the windows could make the virus spread faster. But one thing for sure, whether you're sitting in the back, in the front, in the middle, or the back, no matter where the person infected is, definitely opening the window make it the whole thing getting a lot faster and everywhere getting the virus.
Yeah, I'll throw in a final comment. I think there's a lot of things that we learned in this study that were counterintuitive. We thought when we went into this study that certain things were going to work, and we found that they didn't. And so I think what this study has done is just show us that we need to do more study. There's actually quite a bit of additional research that should be done in this arena to really kind of answer all of these questions, not only the questions that folks pose today, but the questions that have circulated in our minds as the ones who were actually involved in this work.
Great point. And the last question, so Joseph, the person who just spoke, is the person who is with Fresno Metro Ministry. So Joseph Oldham is with Fresno Metro Ministry. So he's the person who gave the welcome introduction, and he's the person who's also going to give the closing and thank you. Looks like we have another question in the Q&A from Kristen Mazur. As you know, here in California, we've been struggling to deal with both COVID and wildfire smoke. Would all of these air filtration systems also help with wildfire smoke? Mo, do you want to take this one?
We do not know, to be honest. We absolutely do not know that. However, I will be leaning to believe that any type of HEPA filtration could help dramatically with smoke. But we cannot tell for sure it could help or not. That is need to study the nature of that smoke, the nature of the debris flying with the smoke, and that was not the focus of the study. So the short answer, we don't know, really.
Great question. Sadly, we cannot help. All right, so I think I've covered all the questions in either the Q&A or in the chat box. If I missed anyone, please write it down.
I have a question, actually.
I saw that you wrote a question in the chat box. I just
for Dr. Yuri, actually.
Yeah.
So maybe you can say it.
Yeah, so the question is how similar is Phi-6 to that of the flu virus?
Okay.
So actually, the flu virus is scary, and this is why we always get vaccines every year, because although Phi-6 is similar in size and structure to that of the flu is its genome is actually split into 8 different parts, and so it rearranges really easily. And so as it infects a cell, you can actually get different viruses infecting a cell, and they can rearrange their genomes. And so this is why the flu virus just changes so rapidly. And that's why we have different vaccines that we have to get every year. So although Phi-6 is similar to that of the influenza virus is actually really complicated by comparison.
Thank you.
All right, we have another great question from anonymous attendee. Do you think the findings regarding windows is applicable beyond buses? I'm thinking about, say, a classroom space. That's a great question. I will take a step and then I'll open it up for anybody who wishes to add. So our results with windows opened and windows shut were different when this bus was in motion or stationary. So when the bus is in motion, when you open the windows, this helps the spread of the virus inside the bus happen much faster. When you open the windows, when the bus is stationary, it does the opposite, also only marginally, because the size of the windows in the buses is very small. And how the windows opened also affected. So some windows were tilting inwards and some windows were sliding parallel to the wall of the bus. So this also had different impacts. So, so is it applicable beyond buses, example classrooms? My intuition is I don't think we can be for certain unless we actually do the actual experiments. Any of the team wish to add to that?
Let me just throw out a comment about that. So what really, we're learning with this virus is, first of all, that it is airborne and it is very small and it will circulate quickly and stay suspended in the air. And depending on the position of the windows, depending on the airspeed, the wind speed outside, how much ventilation is actually going through the building, I think it's all going to be extremely important in understanding whether the virus is going to spread quickly inside of a building or settle on surfaces and all of that. So I think, really this begs further investigation and further research. But at the end of the day, I think what it's going to turn into is it's going to be ventilation dependent, and areas with higher ventilation and positive air pressure will probably be beneficial. And then of course, incorporating the mitigation technology into the HVAC system to kill the virus once it's actually in the HVAC system is going to be crucial.
I want to say that the HVAC physics are pretty much the same between the buses and the home or residential buildings or classrooms, like classroom spaces. But with like Dr. Toffee said, we still have to do more experiments to verify that.
I also want to add that really opening the windows in a stationary position, obviously in a moving position, make a huge difference in the spread of the impact. But on the stationary position, we noticed little to no difference without the positive pressure. So without the positive pressure, opening the window really make little to no difference at all into the or the mitigation of the virus.
Thank you. Great question. All right. So, so this one, do you think beyond buses? This one we answered. So Stoyle asked a similar question. How does the finding about opening the windows apply to all recommendations for commercial buildings to open windows as much as possible?
I can take this one.
Sure.
No, it's an inconclusive. Without a positive pressure into the building, opening window will not have any effect, or at least that's what we found. Opening windows without any positive pressure did not help at all. It could actually work against if you have a negative pressure. So we can't really say that's a recommendation without a positive pressure.
Thank you. Next question by Gino, and I think Dr. Lowe can answer this one. Can you provide details on how the windows opened on bus A and bus B?
Sure. The bus A had small sliding windows, about larger fixed windows. So you're located at the corner of that larger fixed windows. So it's not open with a large areas, but at least still have some openings. Whereas the bus B has somewhat larger bottom hinge windows, about large fixed ones, and it open inward at the top. So the windows slide inward from the top. So yeah, that's my answer.
Thank you, Dr. Lowe. All right, I don't see more questions in the Q&A. There's a comment from Kristen saying that my answer should just be, we don't know, and yes, we do not know. But we're pursuing more grants, and we hope that we can answer some of these questions. All right, there is a question in the chat box. Just making sure I did not miss any, from Henry Pan. When the buses were stationary, how did the different window open positions, tilt, slide, impact how much slower the virus spread? I'll take this one. We did not, in our experiments, we did not notice when the bus was stationary, and we did not, and the difference pressure between the bus and outside was almost neutral. We did not notice any difference, any impact, for any significant impact for opening the windows. Mo, do you want to add to that?
Yeah, I was going to actually say the same. When the bus was stationary, it doesn't matter how the window is open, tilt, open, slide. It did not have any impact whatsoever, or at least that impact that noticeable or we can record it. And also, I mean, I understand that we didn't answer all the question, but that is the nature of any scientific research, that we're not going to have answers to all questions. That is why we need further studies, but at least we answer some questions and some important ones.
Yes, this study, by the way, was complete. So all this work was done in less than 5 months. So from the inception of the idea till today is about 5 months.
Yes.
Dr. Toffee, I want to address one question posed by Mr. Brian Sherlock in the press release 2 days ago about the air changes per hour. So for the bus B, the air changes per hour was measured to be about roughly 29 air changes in 1 hour. For bus A, it was found to be around 20 air changes in 1 hour.
Thank you, Dr. Lowe. I do not see any more. Thank you, Kristen. Thank you all for your kind words. We hope that this, I mean, our objective was we wanted to be as helpful as we could. And that's the reason we decided to release our results early before completing the final work and the reports, is because we thought they could be helpful. So I do not see any more questions. If anybody has any questions, feel free to contact us. So we're always happy to help in any way we can. And with that, I'll turn it to Joseph for final words.
Well, yes, thank you, Dr. Tawfiq. Yeah, this has been a great project. As he said, it was very quick. We had about 5 months to do this. We had an amazing team. I'm just so blessed to be a part of this work. Everyone got along so well, and we had so much cooperation from Fresno County Rural Transit and Clovis Transit. Their support and contribution to this was indispensable. We couldn't have done it. So thank you all again for tuning in today, and glad I'm seeing a lot of the comments coming up. People are appreciating the work that we've done, and that makes us all feel very good. But more importantly, we're all just in this fight together. This virus doesn't care. It's going to infect anybody that's a human being, and we're all that. So, we want to make sure that we can protect our modes of transportation as best we can to allow people to carry on their lives as normally as possible. And we'll all get through this, and we'll work together. And this is a prime example of how you do that. So thank you again for attending today. And again, as Dr. Tawfiq said, if you have any other questions, don't hesitate, reach out, and we'll see what we can do to answer them. And well, thank you again. We'll hopefully have some new results here in the not too distant future from some additional research. Okay, thank you all. Bye-bye.